This is the example that we're talking about. 1532 says for the Colpitts oscillator of figure P1532, which is this one over here, derive an equation governing circuit operation and hence find the frequency of oscillation and the condition, the gain GM times RL, so that would be the GM of Q1, must satisfy to ensure that oscillations will start. And then assume that RO, that's the output resistance of the transistor, is included in RL, so that is convenient. But essentially, as I mentioned, RO is going to be much higher than RL, so the overall, and RL is in parallel with RO, so the actual value of that parallel combination is going to be very close to RL, so that's not a bad assumption. Also, they allow us to neglect RF, which is essentially saying, hello? Was that a question?
No, sorry, I forgot to leave.
Okay, but you all can hear me okay, right?
Yeah.
All right, very good, very good. That's the important thing. So they are allowing us to neglect RF, which is essentially saying that RF is much higher than the reactance of the inductor. And then they just say that the circuit is based on the classic Colpitts oscillator of figure 15.14a. All right, so now what I'm going to do, I'm going to switch back to my pad. So again, this is problem 1532. So I'm not going to write again the assumptions, but we're going to start with a small signal model of that circuit once we take into account all the accommodations that they told us to make. Essentially, RO has been absorbed into RL, and RF can be ignored, as well as those capacitors that show a value of infinity that are there just from correctness and elegance perspective to model the capacitance of the transistor at the terminals. But the practical small signal circuit that we get is this. So here we have C2, and this node over here is the gate of the transistor. Then we have the inductor to the drain. So this is L, this is the drain. And then at the drain, we have our transconductance. So that is our voltage control current source. And that is going to ground. And this is C2 here going to ground. And here we have C1 and also RL. And in the ground node, for the small signal equivalent circuit is the source, which is biased. So that's where we start. So then the first thing that we did, is to write a couple of node equations. So the first node equation that I'm going to write is at the gate of the transistor. So we get VGS minus the drain voltage divided by the impedance, the Laplace impedance of the inductor, plus VGS divided by the Laplace impedance of C2, and that is going to be equal to 0. That I'm going to call that equation 1. All right, so now I'm going to make some space here. Then the next equation is going to be at the drain. And for that, we have that VD minus VGS divided by the Laplace impedance of the inductor plus VD divided by the Laplace impedance of C1 plus the current source, that's GM times VGS. Then lastly, the current through RL, that's equal to 0. I'm going to call that equation 2. And I'm not, just like I did in class, I'm not going to show all the algebra, but I'm going to give you the steps. What you would do at this point is solve for VD in equation 1 and substitute for that solution of VD in equation 2. So we normally solve first in the simplest equation, in this case equation 1, and solve and substitute in the more complicated one to get rid of, in this case, VD, because we just want to have an equation with what we would consider the input of the amplifier, and this is a common source amplifier. That's why we were able to say that the source was a ground for the small signal model. And the input of a common source amplifier is at the gate, in this case, VGS. So we substitute in equation 2. If you do that, then you get S C2 VGS plus SC1 times 1 plus S squared L C2 times VGS plus 1 over RL times 1 plus S squared L C2 times VGS plus GM VGS equals 0. So notice that VGS, the input, which is the same as the output because it's an oscillator, is in every term. So we can divide by VGS and get rid of it, and essentially we're getting the characteristic equation of or the loop gain equation of the system. So when we do that, so we say divide by VGS and collect terms, we get S cubed L C1 C2 plus S squared L C2 divided by RL plus S C1 plus C2 plus GM plus 1 over RL, and that's equal to 0. So we get that is the loop gain. So we get a nice polynomial on S, a third order polynomial. And then the next step is to replace S for j omega and separate. Now that we have a complex equation, we're going to separate the real and imaginary parts. Okay? And then when we do that, we get j omega times minus omega square L C1 C2 plus C1 plus C2. So that's the imaginary part. And then the real part is minus omega square L C2 divided by RL plus GM plus 1 over RL equals 0. So I notice that at least in this term here, this is a conductance, GM, and 1 over L is also a conductance. So it gives me some validation that the units and the type of quantities are matching. So that's nice. And then we said that for this procedure, one part will give us the frequency of oscillation and the other one will give us the condition of oscillation, which must include the gain. And I see that they mention that the gain is GM as it is for a common source amplifier, GM times RL. So I see that those two quantities only appear in the real part. So I don't have RL or GM in the imaginary part. So the imaginary part is the one that must give us the frequency of oscillation. So I can say imaginary part equals 0 gives the frequency of oscillation omega naught. And then if I solve this, if I equate this, this is the imaginary part. Of course, the J is implied. I don't have to have the J, or it should not have the J. If I equate that to 0, which is doing this, then I get that, and substitute for, instead of omega, it's going to be omega naught, because that's the frequency of oscillation, because the condition is that that imaginary part is 0. So for that to be valid, that means that that's valid at the frequency of oscillation. So then I don't have omega anymore, I have omega naught. So I just substitute omega naught instead of omega in that part and solve for it. Then I get that omega naught is 1 over the square root of L times the series combination of C1 and C2. So remember that capacitors in series, we lump them like resistors in parallel. That's a nice thing to remember. So C1 and C2 in series would be C1 times C2 divided by C1 plus C2. And that is our frequency of oscillation, which I'm going to call equation 3. Then the condition for oscillation is found by equating the real part to 0 and using equation 3. So what that means is that I'm going to, in the real part, which is minus omega square L C2 divided by RL plus 1 over GM plus 1 over RL. That must be equal to 0, but then since we are at the conditional oscillation, this omega is omega naught, which is equal to that 1 over the square root of L times C1 times C2 divided by C1 plus C2. So this goes in there, and then all I have is an expression that includes the components, and if I solve for the gain, which is specified to me by the problem as GM times RL, so once I do that, I need to isolate GM times RL. Okay, so what is that from this equation over here? Well, a lot of things are going to go away and cancel out, and essentially you'll get a very elegant solution that GM times RL is just the ratio of the capacitors. So we would say that what this implies is that we must make GM, the gain, higher than that ratio, because this is where it's 0, but we wanted it above 0. We want it greater than 0. So if we make GM times RL greater than that ratio, we ensure oscillation starts. And that is the solution to to problem 1532.